everyone, and thank you for joining today's session. I'm Miruna Zala, Market Development Manager, and I'm excited to be part of this insightful and thought-provoking webinar organized by Smithers today. I will touch upon about high-performance additives for textile upcycling and the circular economy. So I will give you first a quick overview about Kraton, because I don't know how many of you in the room are familiar with us. Then I will briefly touch upon key trends in the textiles and fibers industry. I will also talk about how Kraton creates value creation through innovation. And I think given the time, I'm not sure if there's going to be enough time for the Q&A session. So about Kraton, we are the inventor of styrenic block copolymers and a global leader in specialty chemicals. Headquartered in the Woodlands, Texas, we operate 12 manufacturing sites and 7 innovation centers globally. Our mission is to create innovative solutions for a sustainable tomorrow. This year marks the 5th consecutive year of Kraton receiving the EcoVadis Platinum Sustainability Rating, which is a true testament of sustainability being central to everything that we do here at Kraton. We are also an active member of Together for Sustainability, as well as the regional recycling plastic associations. We also have a global footprint of IACC Plus certified manufacturing locations. Kraton focuses on market-driven innovation to help our customers address key industry challenges across a broad range of end-use markets. Our products serve a wide range of industries, from automotive and medical to paving, roofing, and, of course, textiles. Now let's take a moment to talk chemistry. Our products are known as styrenic block copolymers, or in short, SBCs. In their simplest form, they consist of 2 hard polystyrene end blocks covalently attached to the rubber mid block. Because the hard polystyrene blocks are incompatible with the rubber phase, they phase separate. The result is a microstructure where small polystyrene domains are dispersed through the rubber matrix, as shown on this picture here and on the 10 micrograph below. These hard domains act as physical cross-linking points, giving the material the elasticity and strength of a cross-linked elastomer, without the need for chemical curing. At room temperature and below, SBCs exhibit excellent elasticity, high elongation, tensile strength, and the ability to absorb a lot of impact energies. The products can be melt processed like thermoplastics, such as polyethylene or polypropylene, and this duality places them in a unique category known as thermoplastics elastomers. We offer a broad solutions of SBCs, from unhydrogenated, hydrogenated, and functionalized, each tailored to meet specific performance requirements. It's important to note that our SBCs are typically used as modifiers within other polymer systems. For example, they may be added to nylon or polypropylene to enhance flexibility, impact resistance, or processing behavior. The choice of the product depends on the base polymer, desired properties, and processing conditions. So while we produce many types of styrenic block copolymers, this presentation today will zoom in into case studies where our Circular Plus product range series has been used. This range consists of versatile high-performance additives targeted to enhance the PCR performance and to compatibilize mixed or contaminated recycled streams. Both compatibilization and performance enhancement series are effective additives with a wide range of materials, as shown on this slide. But now I would like to first take a step back and look at a little bit of the bigger context in which these innovations are being applied. So fashion is more than fabric. It's expression, identity, and it's emotion. It's how we present ourselves to the world, how we feel when we walk into a room, and how we connect with others. It makes us feel beautiful, elegant, and confident. But as we've discussed today, and as we move towards a more sustainable textile and fiber industry, it's important to recognize the complex landscape of challenges we face. On one hand, there is the sustainable design. There are a lot of movements that are taking place at the moment. So for instance, there's the industry shift toward design for disassembly, so basically having fewer components. And there's a growing push for monomaterial constructions, which makes sorting and reprocessing more efficient. And of course, the incorporation of recycled materials shouldn't be a niche anymore, and it should become a baseline expectation. But on the other hand, we are also faced with consumer expectations. And what we see is that today's shoppers are more informed and more demanding. They want transparency, eco-conscious options, and ethical sourcing. Yet, they are also navigating the pressure of fast fashion and often show limited willingness to pay a premium for sustainability. And finally, there's the challenge of functionality. Sustainable materials shouldn't be only eco-friendly, they must also be beautiful, durable, and versatile. And recycled fibers need to perform just as well as virgin ones. And hybrid material, while innovative, they can complicate recycling and end-of-life processing. So this is why the textile and fiber industry stands maybe at a pivotal moment when it comes to sustainability. And one of the most pressing issues is probably mixed fiber composition. While having different types of fibers blended together, they can bring performance and comfort. They are a little bit of a hassle when it comes to recycling and reuse. And addressing these issues requires the industry to have a new approach in how they design, how do they sort, and how they work within the material science segment. There is also the limited recycling infrastructure, and scaling up these systems is essential for waste reduction, but also for building a truly circular economy. What we are seeing with recycling textiles is that downcycling remains a common outcome and reduces them to lower value applications. But what if we could reverse that trend? What if recycled fibers could be engineered to retain or even exceed their original performance? And then there is also the topic of recycled content at scale. This demands consistency, traceability, and trust across the value chain, from suppliers to brands to consumers. And finally, we also see the imperative of carbon footprint reduction, which we have discussed in the presentation before. These challenges are real, but they are also opportunities, and we probably should look at it as opportunities that can help us to rethink how we design, produce, and value textiles. At Creighton, we see these challenges not necessarily as roadblocks, but as opportunities for innovation. And this is where Circular Plus solutions can come in very handy, because they can help address some of these issues, bridging the gap between sustainability, performance, and consumer appeal. So please keep in mind these challenges, as I will take you through some real case studies using Creighton Circular Plus additives. So as we move forward, I will take you through different case studies where I'm going to show you some of the performance data behind our Creighton Circular Plus additives and how they enable compatibilization, mechanical performance enhancement, and processability improvements in recycled textile and fiber systems. So for this first case study, to give a little bit of context, polyamide or nylon, which is the most used synthetic fiber, made up 5% of the global fiber market in 2023, which is about 6.7 million tons produced globally. But due to technical recycling challenges, recycled polyamide, in fact, makes up only 2% of the total polyamide market share. And in certain applications, it has to be mixed with elastan, which is also a material that is valued for stretch and flexibility, but remains very difficult to recycle. So here we have a case study where the customer was looking to reuse their post-industrial waste of mixed nylon and elastan blend in a ratio of 76 to 24%. The answer to this challenge was our solution, which was Circular Plus C1010 at a low loading level of 5% in this blend. Our solution enabled zero waste recycling by allowing the complete reuse of post-industrial waste, while enhancing material stability to ensure durability and consistency in the final product. So let's look at the data behind this case study. On this chart, I have plotted the baseline performance of the recycled polyamide with elastane, which is shown in the graph in blue. In orange and gray, you can see the performance when two of our additives are added. In orange, here, you can see the performance when we add into that blend 5% of C1010, and then in gray, you can see the performance when we add 5% of C2000. By adding 5% Circular Plus C1010, what we've observed was really fantastic in terms of the mechanical properties. So we've seen 1.1 times improvement in tear strength, A 2.2 times melt flow improvement, thus enhancing the processability. And then lastly, we have also seen a 2.4 times elongation improvement, basically contributing to flexibility and durability. And you see here, I'm also mentioning formulation efficiency, which is basically about the fact that being such a low additive loading, it's a very cost efficient approach. So here's another data set. So on the left, we see the tensile behavior of the unmodified nylon elastane blend. And here we are still talking about the same blend with recycled material, which was in the 76:24 ratio. The variability of across specimens highlights the instability of the material, making it unreliable for consistent product performance. But now let's compare with the other graph on the right. When we add 5% C1010, the tensile stress and strain curves become more uniform, as you can see here. This indicates improved material stability, higher tensile strength, and of course, a better process control. So what does this mean in practice? It means that challenging recycled feedstocks, like post-industrial garment waste, can be transformed into durable, high-performance materials, ready for reuse in textiles, apparel, and beyond. So as we go to the next case study, here we worked together with the brand owner to enable the incorporation of post-consumer recycled feedstock for the development of sustainable clothing. For example, this beautiful blue sweater shown on the picture. Here we leverage the power of our Circular Plus additive solution in a very interesting and unique feedstock source. It was the recycled polystyrene that was coming from single-use party cups combined with virgin polypropylene. And I think this case study is beautiful because it illustrates our key value propositions to the industry. By increasing the post-consumer recycled content, we can help brands reduce the need for virgin resources and support a circular fashion economy. And also, by going beyond polyester, we can enable brands to choose from a broader selection of sustainable feedstocks, opening new possibilities for eco-friendly designs without compromising on quality or versatility, and allowing plastic waste to be diverted from landfilling on ocean pollution. So now let's switch gears from fashion and look at another source of waste. And here I'm talking about textile waste that comes from carpets. So one of our customers wanted to incorporate more recycled carpet materials into their products. But there was a problem. The recycled carpet waste stream, once processed, just didn't have the mechanical strength they needed for their applications. So here, because of the material combination, we recommended C1000 as a compatibilizer. So again, it was a low loading level of just a 5%. And we compounded or could also be dry blended with post-consumer recycled polypropylene and nylon right before injection molding. First, using C1000 allowed them to significantly boost the amount of recycled carpet material they could use, meeting their sustainability goals. But beyond that, the mechanical properties considerably improved. And here we are not talking low numbers, we are talking about up to 6 times increase in impact strength, along with a much better balance between stiffness and toughness. So a little bit of data. So as you can see here, we are seeing a remarkable effect when we add our C1000 additive. So when added to both, there's two different combinations. So we have a combination with post-consumer polypropylene and PA6 and LDPE and PA6. So in both situations, we are seeing a significant increase in the impact strength. And basically it shows how it can really help boost performance in different polymer blends. Even more impressive is that this boost in impact strength came with a minimal reduction in the flexural modules, which means that we were able to achieve a better balance between toughness and stiffness, which is critical for high performance applications. So another example in the carpet waste topic. So here we have a complete different waste stream, which is based on polyamide 6 and polytrimethylene terephthalate of, in short, PTT, which again, they are difficult to recycle due to the mixed composition and demanding mechanical requirements. Our customer again wanted to improve mechanical properties of the recycled blends, and we introduced our solution at below 5% based on Circular Plus C1010. And what we've experienced and what we've shown to the customers is that we were able to allow higher recycled carbon content, helping divert more material from landfills. We achieved up to 34% increase in stiffness, which is critical for the structural integrity of the application. And the formulation delivered an overall enhanced balance between impact resistance and rigidity. And finally, we saw a significant increase in tensile strength and elongation at break, which translates to better wear resistance and basically longer product life. So as we mentioned before, our goal was to enhance the homogeneity and mechanical performance of this PA6 and PTT blend. And in this graph, we are showing in dotted gray line the baseline performance, which was the PA6 PTT blend in 45 to 55% ratio. And then in blue, it's the performance when we add C1010 at 5%. And then in green is when we add C1000 at 5% to that recycled blend. So to summarize again, we do see a significant improvement in properties. So 1.4 times increase in tensile strength, a 1.3 times increase in flexural modulus, and a 1.3 times improvement in impact resistance, and overall improved homogeneity of the blend. So you may wonder why there is a picture with automotive applications. So I think this comes back to the discussion that we've had earlier in the presentations earlier about hemp. So this case actually highlights how our solutions can support the integration of natural fibers across a wide range of applications, including automotive. So in this slide, we are looking at how our additive supports the growing demand for lightweighting and carbon footprint reduction in different polymer systems, particularly through the use of renewable natural fibers like hemp. So here the customer, what they wanted to achieve was to replace traditional mineral or glass fillers with a more sustainable alternative, while again not compromising mechanical performance. So here our solution was based on compounding less than 10% Circular Plus additives into a natural fiber polypropylene blend. And what we've achieved by doing that was superior impact strength compared to the conventional polypropylene and talc blends, while maintaining a balanced profile across other mechanical properties, an increase up to 20% natural fiber content, a lower carbon footprint, and most importantly, approximately 14% weight reduction. So this slide showcases how Kraton Circular Plus C1000 and C2000 modifiers can significantly increase the performance of polypropylene and hemp blends, offering a sustainable alternative to mineral-filled systems. Our goal was to compare the mechanical performance of natural fiber-filled polypropylene against conventional PP and talc formulations, which are very typical for automotive industry. And I think, as you can see here, the results speak for themselves. So we've used as the baseline 80 to 20% ratio of random copolymer polypropylene and talc. And then we introduced two Circular Plus formulations in different ratios. So a 5:1 ratio of C2000 to C1000 and a 7:3 ratio of C2000 to C1000. So if we look here on the ease of impact resistance, the trend is very clear because both formulations exceed the impact strength of the baseline blend, and the radar chart further shows the improvements across the key properties such as ultimate elongation, flexural modules, melt flow rate, and impact resistance. So basically, these enhancements make the modified polypropylene hemp blends suitable for injection molding and other demanding applications, while also delivering lightweighting and carbon footprint reduction benefits. I think given the time, I will not go into all of the details of this slide, but basically is another angle where we can look at adding hemp in different system by using Circular Plus. And then I hope that today I was able to show you several case studies using our technology, and I think we can all echo that sustainability is more than a goal, it's also an ongoing commitment. So with our circular plus additive technology, we aim to improve material performance while supporting circular solutions. And this includes transforming mixed fiber waste into durable, high-value products and enabling the use of recycled content in different applications. Basically, to wrap it up, at Creighton, we believe that to truly advance in the circular economy, we need a holistic approach to end product life cycle. Our solutions can help our customers advance their sustainability journey with recyclable design, increased use of recycled content, and extended product life and durability, and lowering the carbon footprint. So thank you for your time, your attention, and your commitment to a more sustainable future. And I look forward to continuing the conversation and exploring if and how we can work together to make circularity a reality. So